Let's talk about one approach to parameter estimation called maximum likelihood, or MLE, maximum likelihood estimation. I will argue that it is a machine learning problem, and all we need to do here is estimate probabilities. Setup, just flipping a coin. I have a coin. If I flip it, what's the probability it will fall with heads up? Okay, should be recording correctly. So let us flip it a few times to estimate the probability. In this case, we flipped penny 5 times, and we see it landed heads up 3 out of 5, and it landed tails up 2 out of 5. And then we usually say, oh, the estimated probability of a coin landing heads up is 3/5 frequency of heads. That's, I assume, what you would say. But now ask yourself, why frequency of heads? How good is this estimation? And why is this a machine learning problem? Let's go ahead and answer these questions. So, first question, why frequency of heads? Why frequency of heads is the probability of the head landing heads up. Well, frequency of heads, and we will see it now, is exactly the maximum likelihood estimator for this problem. Maximum likelihood estimator has nice properties. Well, and it has bad ones too, but that's another story for another class or another lecture in this class later. So let's start with our MLE, maximum likelihood estimation. Maximum likelihood estimator for Bernoulli distribution. Our data is our coin flips. And so we keep flipping a coin until we get tired 5 times and we're done. Our data is a set of those observations, and each observation or each sample is either a head or a tail. We can denote, we can also denote 0, 1 or something like that. So an interesting thing about this distribution is a certain symmetry, because it's either a head or a tail. Probability of heads is some parameter, but probability of tails is 1 minus that parameter. Well, that's symmetric. We can sweep the data parameter, and 1 minus 1 for heads or for tails, depending on what you declare is most important for you or more important. Doesn't matter. So those are our probabilities, and we make an assumption that our flips of the coin independent and identically distributed. That the first one means that the next flip does not depend on the previous flip. It's just as random as before, and identically distributed according to the Bernoulli distribution just means that every time we flip a coin, our parameters don't change. They are the same. The sample comes from the same distribution. That's generally true in our universe, but maybe like after a few years of flipping a coin from friction and from temperature changes, it affects the theta parameter, but we are going to ignore the physics of it. And especially in this example, we're just identically distributed, means that the distribution doesn't change as the sampling proceeds. Maximum likelihood estimator says, or the task of estimation is we need to choose a theta such that it maximizes the probability of observed data. This is this whole likelihood approach. We need to pause here for a minute. So when we wrote our Bayesian posterior distribution or the Bayesian formula, right? We want to see, given the data and the data what we're collected, we want to find out probability of theta given our data set. But what we know rather is probability of our data set once the theta is fixed. So if we are given a theta, then we know how to compute the probability of observing our data set. Yes, okay, so if we write this distribution right here, we would say this is called likelihood. And the main point about the likelihood is, well, a couple. First, it's a conditional distribution. If you pin this parameter, if you fixed it, then it's a conditional distribution. And then we can say, okay, for this value of the parameter, how likely we are to see this data set. So that's what the likelihood tells us. Well, not quite. That's what the conditional distribution is telling us. But the likelihood is not a function of the data. Data kind of stays the same. The funny part is that likelihood is a function of the conditional, the variable that we condition on. So we are saying it's a function of this variable. Keep changing this variable and it'll give you a different value of how likely this data of probability of how likely this data came from a probability density with this value of parameter theta. So the likelihood is a function of parameter, and since this parameter is this conditional, the variable at which the probability density is conditioned, likelihood is not a probability density. It doesn't have to integrate to 1 and have other properties of probability densities. So pay attention to that. Okay. Still at the maximum likelihood estimation. And our task is to choose or find theta that maximizes the probability of observed data. So what we do, just formulate it in step by step in the mathematical terms. This is our probability of the observed data given the setting of parameters. This is the likelihood function when considered as a function of theta. And we want to maximize this likelihood or find a theta that maximizes the likelihood. Such theta will be our maximum likelihood estimator. For independent draws, since our draws are independent, we assumed IID, remember. Our total likelihood is just their independence, so it's a product of likelihoods for each individual sample. Remember our initial section about independence. The distribution, the joint distribution of D factors into distributions of individual samples. But for this Bernoulli variable for the coin flips, what we have here, we can split it further into two parts. One product of just theta when it's the head. For all of the heads, we group the product of the heads here. We don't, this is just manipulation of symbols. We just do it for convenience, and you'll see why. So they're independent rows and they're identically distributed. So we have heads and tails, probability of tails 1 minus theta. That just the value of this distribution for tails is this, for heads is that, the value of actual probability. And but look at this, we have alpha sub h of heads, and we have alpha sub t of tails. And that's what we're maximizing now. We need to maximize theta power number of heads times 1 minus theta power of number of tails. Still at that, choose theta that maximizes the probability of observed data. And let's proceed. So, well, I denoted the J as objective. It's often denoted by L as the likelihood. So we need to maximize this function. And let's just go the usual calculus way. The function is maximized where the gradient is 0. So let's compute the gradient of this expression with respect to theta. So yeah, we'll just differentiate this by the product rule, right? Derivative of this first, here you go, and then derivative of that part, minus derivative of this part. The minus comes from minus theta there. Otherwise, it would have been a plus. You can just follow through the steps. What are we doing? Grouping the steps accordingly. Yes, so let's take this and this out. So what's left here is just that. Well, alpha sub t minus 1 we took out. So there is no exponent here. And theta power alpha sub h minus 1 we also took out, so there is no exponent here. Well, now look at this expression. This expression, if it's 0, then of course the gradient is 0, but it can only be 0 in a non-interesting way. It can only be 0 if theta is 0 or if theta is 1. See if it's 1, 1, 1 is 1, or if it's 0 here, but that means it never falls on the heads, or like it never falls heads up, or it always falls heads up. That's another interesting case. That's we better not waste time on, and let's just look at what's left and see how this part can be equal to 0 in an interesting way. So we can what do we get here? Of course, some trivial. Oh, okay. trivial algebra, I want to say, and I think I'm right. Minus theta alpha sub h. Okay, that's true. That's true. And that's true. Okay. And okay, now it's easy. We can just take it to the other side, and we got our estimator. So, and our maximum likelihood estimator of parameter theta of probability of landing heads up is exactly the frequency of heads as you see here. Yes, indeed. So, okay, we showed, or I hope you're now convinced, or at least you understand why frequency of heads is the parameter theta probability of the coin landing heads up, because it precisely maximizes the likelihood. Well, let's go to our second question. And our second question is, how good is this estimation, right? So we established that this is the maximum likelihood estimator, frequency of heads, for the Bernoulli coin. But how good is it? So how many flips do I need? So if I flip the coin 5 times, 3 heads, 2 tails, my estimator of the probability is 3/5. Is it good enough? Is it not good enough? If I flip 26 heads and 24 tails 50 times, then it's 26/50. Should I keep flipping? How many times should I flip in order to get to a good estimate? Which estimator shall we trust more out of these two? Okay, let's assume, I think it's fair to assume, and it's easy to see, that there is a true parameter, theta star. Let's establish a simple bound on this. For n equals, where n is number of flips, for n equals alpha h prof plus alpha t, number of heads, number of tails, and maximum likelihood estimator given the frequency of heads. For any accuracy parameter epsilon that is greater than 0, positive, we will use Hoeffding's inequality. And the full form of this inequality has ratio a minus b here, but I'm just explaining it in case you decide to look it up, and then don't be surprised, because a and b is the interval within which your parameter falls, or the value of your individual flip, and our value of individual flip falls into 1, 0, and so 1 square as a ratio doesn't add anything. So we have Hoeffding's inequality for our coin flip problem as the follows. So probability of our estimate to be worse than the parameter, some accuracy parameter. So our remember, probability of error is less than or equal to 2 times e power minus 2 times the number of samples and our accuracy parameter squared. I hope that reminds you our pack learning problem, right? So pack learning, I want to know the coin parameter theta with epsilon equals to 0.1 error with probability at least 1 minus delta of 0.95. So I want my parameter to be within 0.1 of the true parameter 95% of the time, right? So if I want this properties of my estimate of theta, how many flips do I need? Well, let's use Houghton's inequality. Yes, basically what we say, we want her probability of getting further than 0.1 from the true value of the parameter. We want this to be less than or equal to delta in order to meet this criterion. And now you can yourself rearrange and compute how many samples you need. Yeah, so many samples, very easy. Again, we compute this. So how did we get there? We just looked at this part and what took a log of it. Okay, yes, what do we have? E minus the n epsilon squared divided by 2 both parts. So we got delta over 2. Then took a log of both parts, 2n epsilon squared. Log is a monotonic function, so it doesn't change the sign. Log of delta over 2. Then what do we do? Let's divide by minus 2 epsilon squared because it's a negative now. We're flipping the sign, so we get n. So divided by minus 2 epsilon squared, it cancels here, and we get here log of delta minus 2 epsilon squared. Take this minus, take it inside here, 2 over delta, and that's how we'll get this. So now plug in the delta value 0.5, plug in epsilon value 0.1, and so you need approximately 150 flips, coin flips or samples if you want to get 95% of time. You want to get within 0.1 ratio of your true estimate, of your true value. Okay, if you well, technically when I plug it, when I plug those numbers in, I get something closer to 184. Okay, so we answered the first question, I hope, which was how good is this estimate, right? How good is this estimation, or how good is this estimate? And Now, why is this an ML problem? So what is machine learning? Right? I refreshed from our first lecture. Machine learning is the study of algorithms that improve their performance at some task with experience. Well, what about our maximum likelihood estimate of the uh, probability of coin landing heads? It improves, right? Accuracy of predicted probability improves. With experience, well, the task is predicting the probability of heads, and the experience is the more flips, the better the estimate. So a lot of problems are metaphorically, a lot of machine learning problems are metaphorically concentrated in this simple problem of estimating probability of heads in a coin flip. But when you deal with more complicated problems and tasks in machine learning, you're basically facing similar problems and using often similar approaches, like maximum likelihood approach for estimation is prevalent because it's so simple. Well, fine. Bernoulli distribution, easy. We can compute the backbound. We can estimate sample complexity, but what about continuous features? What if we sampled one-dimensional points like those pink circles, and we want to estimate Gaussian distribution that generated those points? And remember, estimating Gaussian distributions requires estimating just a couple of parameters, mu and sigma, mean and variance, especially for this one-dimensional case. So let's try Gaussian, right? Probability of x given mu and sigma is given by this functional form. And this is a standard notation for a Gaussian distribution, normal distribution with mu, mean, and sigma. For multidimensional, of course, mu will become a vector, and sigma will become a matrix, covariance matrix. And a regular Gaussian distribution. How do we estimate the parameters of the likelihood given data? So maximum likelihood for Gaussian mu and variance, sigma squared. Just find the theta, which is a combination of mu and sigma squared, that maximizes the probability of observed data. So basically, we need to feed the distribution or the function, the likelihood function. Well, I take that back. We need to feed the distribution, Gaussian distribution, to the data such that the probability of this data coming from Gaussian is maximized. So we need to maximize the likelihood function. And again, we use the same assumption, IID. We need to find theta that maximizes the likelihood. Our likelihood is Gaussian, but it factors because of independent draws. So we have a likelihood of each of our data samples, product of those likelihoods. There are IID, independent, identically distributed. But if we look at it now, that this coefficient does not depend wait a second. So when we multiply n of those, and this is as good as Yes, we can rearrange this part and exponent parts into products. Then this together will be power n times product of the exponents is the exponent of the sum. So we have this expression and we need to maximize that. Let's try to do that in a few ways, right? Just yeah. So we have our data set and we are at the ability of our data set given mu and sigma, well, or sigma squared if you want. So what we have is sigma square root of 2 pi, and then we had n of those, or n for all of our samples, and then we have e to the minus 1 to sigma squared, and the sum of xi minus mu squared. So now our goal is to maximize that expression with respect to mu. So find mu, that is but notice the this coefficient doesn't depend on mu, and since we have a square here, no matter what xi and mu values are, we cannot get the e to the power something. Of course, we cannot get to negative. We cannot like we can only minimize. We can maximize this whole expression, but by minimizing the power of this exponent, because the larger is this part, the smaller is the exponent. So we need to maximize this part. So let's just try it. One. Okay, and I'm doing it as I write. So we want to maximize this with the minus sign. We want it to be as close to 0 as possible, right? Maximizing the negative. And how do we do that? Well, again, we can only do that. This part doesn't matter. We don't control that, but we need to minimize this part. So if we say, let's say some objective function equals xi minus mu, which we want to minimize, we take with respect to mu and set it to 0. Okay. Which for us will be, and I'm just doing the math, minus 2 mu sum of x I minus, okay, and plus n mu squared summed over n times. And we want it to be 0. Okay. Then and we have n mu squared equals to okay. I think after all it was more convenient to keep the -1 to sigma here. I'm just keeping that in because that'll help me to cancel some stuff. I don't like this 2. So 2 and 2 will cancel. And now it's a plus sign here. 2 is gone. 1 over sigma squared. And a minus sign here. Let me destroy that. But 1 over sigma squared here. Now we can get rid of 1 over sigma squared, and like we got it. Mu squared times n equals mu sigma xi, and from this we cancel mu and divide by n, and we get that mu is this. Okay, that's good exercise to do that you can do yourself for variance. Basically, we arrived at our maximum likelihood estimator of Gaussian mean, and it's the familiar sample mean to you. Well, should be familiar, but notice that I've used some kind of tricks, manipulations, properties of products and exponents that may not always be useful. So usually when people work, or may not always be easy, and that's not the dream that Leibniz had when he gave us calculus. The dream was that there will be a simple set of rules that anyone can just mechanically follow and get a result without thinking too much. So we had to think a little bit before. So if we have a Gaussian distribution, now you're a pro or professionals here, right? So we have our Gaussian distribution. What we do usually, instead of maximizing the likelihood, we take a log of it, and log is a monotonic function. So maximizing log of a function is the same as maximizing a function. So we maximize log likelihood, and log likelihood, just reminding you, sigma square root of 2 pi e to the minus x minus mu squared over 2 sigma squared, and then our log likelihood will be log of sigma square root of 2 pi plus x minus squared sigma squared. And again, there was a product here in the likelihood when we took log of a product, we got an n somewhere here. Yes, and I've lost a minus sign. There's 1 minus. Well, I mean, you see that I brought it up, and here we had a log. Now it's a sum. I think. Well, just to be consistent with what I wrote before. I equals 1. Some I mean the same. Looks right to me. Okay. Now we need to differentiate our log likelihood and look how easy or much easy it becomes now with respect to mu nothing here, and we get almost the same thing as we got before without thinking too much. Okay. The same stuff. And of course, that's 2 and minus goes plus, 2 is canceling, and then we just need to minimize or actually solve this again, which I'm not gonna do, but you can. You can do that, or you may try. It would be useful. Another interesting thing about Gaussian distribution is that if you write say this expression and our Gaussian maximum likelihood estimator, what do we have there? X sub I. So this whole Gaussian likelihood can be expressed in terms of two quantities, xi minus mu squared. If we plug them in here, then that's all we need to express this whole Gaussian distribution. There will be no data anymore, just sample mean and sample variance. So for Gaussian distribution, mean and variance are sufficient statistics that all you need to express the distribution. Interestingly, we can compute MLE estimate for the mean, but we can also compute MLE estimate for the variance. But because for the variance, like for the mean, the variance conveniently drops off, but for the mean, for the variance, the mean does not. And all we have right now, based on the data, is our sample mean. But turns out, if you plug in the sample mean into the variance maximum likelihood estimator of the variance, then your estimator turns out to be biased. That's it. It doesn't arrive when in the limit when the number of samples goes to infinity. It doesn't arrive at true sigma squared, but it rather arrives at n minus 1 of the n of the true sigma squared. So in order to compensate for that, we, instead of dividing by 1 over n, we divide by 1 over n minus 1. And then we get an unbiased estimator. because we're using our sample mean in the estimator of the of the closer to the end. So a small refresher: exponential family of distribution. Exponential family of distributions is extremely useful in machine learning because a lot of it's easier to deal with, and a lot of results and a lot of tools are obtained because of exponential families. Distributions from exponential family are useful and often analytically tractable, or at least helpful to reason about and build arrive to some logical conclusions. Exponential family of distributions, any distribution in exponential family can be expressed in a simple uniform way. So you have an exponent of those parameters. So you have multiple functions because we're trying to write the most general form. You have h, you have g, and you have u. So eta are natural parameters of a distribution, and gn is basically a normalization, or g eta is a normalization constant that just says this, or ensures that the following holds. Sorry, first one, that distribution integrates to 1, and u when is some function of u, as well as the h is some u is some function of x, and h is some function of x as well. So using this, you can construct any distribution in like the most, and this is the most general form for exponential family. So interestingly, Bernoulli distribution that we just looked at, which would be, say, heads or tails, one minus heads, because it's either one or another, right? If our heads and tails are 0 or 1, that's our Bernoulli distribution. But this distribution can be readily expressed as an exponential family. The following, you can just this is just an exponent of the logarithm. We're just rewriting. What we got? It's exactly the same. What's written here, and you can do it as a homework. Just yeah, that's our exponential family, very useful family of distributions. to work with. Just of course you know that, but reminding you that we work a lot in machine learning with exponential family distributions and many methods in continuous and in discrete um, space that you already know or you will learn about later are formulated using distributions from the exponential family.